Hello. Hello.
Hello.
Okay, so they have joined. All right. Okay, so am I audible?
Yeah.
Okay, sure. So, hello everyone. Hope all of you are doing very well. So, welcome back to another monthly session where we bring experts from the industry to discuss amazing topics related to data science and AI. And our screen is not visible. I hope it's visible now.
Yeah.
Okay, let me start again. So, should I start again? Is it visible?
Yes.
Okay, okay, sure. So, sorry for all of this, everyone. So, hello again, and hope all of you are doing well. Welcome back to another monthly session. Where is it echoing? Sorry for the lag. I don't know what is the problem here. Okay, starting off again. Really sorry, guys. Is it visible? Is it audible?
I can hear you, but there is nothing on the screen yet.
Uh, I've shared my screen. Is it not visible?
I can just see a blank screen. Maybe you're sharing. Maybe.
Hope it really works this time, guys. Is it visible? Audible? Am I audible? Sutirth?
Yes, I can hear you.
Can you see the screen?
I can just see a green outline rectangle with a black screen inside it.
And
Yeah,
nothing.
now I can see it. Now I can see it.
Um, okay, let me just start. Okay. So, yeah, it's all right. So, let me just start.
So I need to share my screen. Just give me that option to share
Yeah,
my
sure.
screen. That I can.
Hi everyone, sorry there was a technical glitch. You can start. Suritha, I've given you the option. You can share your screen now.
Okay. All right. Thanks. Hello, everyone. Let me just start sharing my screen. I'm trying to find the screen share option on Zoom here. Can't really see it.
You should have it on your option menu. Should be a green button.
Can't really find it. Let me see. Let me do one thing. So I can email the slide deck. So I think that'll be better because I can't really find the screen share
Yeah,
option here.
sure.
That'll be better. I'll just email the slide deck so you guys can just turn over the slides. So I've emailed the slide deck to Harshita. You can just open it from your email, Harshita.
Sutirtha, can you just forward those slides to me? I guess Harshita's internet is not working right now. That's the problem in this. I
Yeah,
just
I
shared you
just,
my email
yeah,
address.
yeah, yeah. So I have just emailed you the slide deck. I mean, it's, let me just try once more.
Yeah, I didn't get it right now.
Yash.Chauhan, right? Yash.Chauhan at insaid.co, right?
Yes, yes, that's it. Yeah, got it. I'll just present it. Give me just a
Okay,
second.
got it. Okay, good.
There you go.
Yeah, just make it full screen and start.
Should I play it?
Yeah, yeah, sure, please. Um, okay, hello everyone. Am I audible? Hello? Okay, good, good. Okay. Well, first of all, sorry about the delay. I know you guys have been waiting for the session, and really sorry about that. And so, talking about today's session, and I think before going to the session, I'll give a brief intro about myself. So, I'm basically a statistician turned data science professional with about 15 years of experience in statistical modeling, machine learning, AI, ML, like AI and its applications across a wide range of. Hello, am I audible? Is it better? Okay, good. Okay, so I'll just start over. So as I was saying, so I'm basically a statistician turned data science professional with about 15 years of experience in statistical modeling, machine learning, AI, across a wide range of real world application fields, like ranging from drug discovery development to more like in human resources, people analytics, health economics, sales and marketing domains, right, and medical devices and health tech as well, digital health, all these kinds of areas. So today I'm going to talk about the long journey that happened from the Perceptron to GPT-4, which is nowadays a hype or a craze. So I just want to set the expectations right from the beginning of the session. So as you can understand, right, this entire journey happened like over, I would say, like 100 years, not 100 years, but at least, yeah, close to about like 70, 80 years. So it's a long period of time. So of course, it's not possible for me to cover everything in this long period of time. So the main takeaways from this session, in my understanding, would be to get a solid conceptual understanding of deep learning, like how deep learning evolved over time and what makes it work so well in various situations, and how this journey actually evolved, from the first basic neural network to something as complicated as GPT-3 or GPT-4. Okay. So saying that, I'll just start. Can you go to the next slide, please? Okay. So it all began with the perceptron, right? And you can see a graphic on the left hand side. I took these graphics from various sources on the internet. So, so the first thing that happened was something called a McCulloch and Pitts neuron, right? Which they came up with in 1943. So this was the first artificial simulation of a biological neuron as we get in a nerve cell in a human brain. Like, so if you remember your high school biology, you would remember that, like, do any one of you remember the biological structure of a neuron, like what it has and all? So yeah, right. So as you know, it has different parts. It has some dendritic cells or dendrites that go into something called a soma, and then that soma connects to a series of axons. Yes, right. And then those axons fire synapses to other neurons, right? So that's the architecture of a biological neuron in human brain. So that very same concept was attempted to like that very. So these guys like McCulloch and Pitts, they were basically, the McCulloch was a neurobiologist and I think neuropsychologist. Yeah, neuropsychologist, and Pitts was a logician. So both of them, they actually tried to emulate that same blueprint of a biological neuron in an artificial environment. And that's what led to this invention, which we know today as McCulloch and Pitts neuron, which is the first artificial simulation of a biological neuron. And this happened way back in 1943. But as you can see in this diagram, so it basically has a series of inputs, or more specifically saying a series of binary inputs, which is either 0 or 1. These are x1, x2, x3 like that. And then these inputs go into a function called g, which is the function that you can see on the left half of this circle on the in the left diagram. And then that function g processes those binary inputs in a certain way, and then there is a final mapping function f that connects that processed input to a binary output y. So this is where it all first began, right? So and you can see the exact mathematical functional form of a McCulloch and Pitts neuron down below that inset. So it's basically like a function sigma x, which is 1 if the sum of all the inputs is over a certain predefined threshold, like which is denoted here as script theta, and there is some thresholding constraint that is given by thresholding switch, I would say, which was a part of this McCulloch-Pitts neuron, which is defined by this I. So if it is 0, only then this neuron will fire. If not, then it will not fire. That's when it will be 0. So these two things taken together represents the architectural and mathematical formulation of the first ever artificial simulation of a biological neuron. Okay, and you can see the pictures of McCulloch and Pitts in the inset. So from this point, cut to 1958. So that's when Frank Rosenblatt. So Frank Rosenblatt was basically a neurobiologist working in Cornell University at that time, and he was doing all these researches with these kinds of simulations and all these kinds of things, and he came up with this first ever implementable model of the perceptron in 1958. So as you can see, right, I mean, the McCulloch and Pitts neuron model was like amazing at that time, but it had several drawbacks. The first thing was, these inputs like x1, x2, xn, they are binary, right? Second of all, these inputs are, they do not have anything that can control their impact on the final output, as in any weights. So the entire thing, as this, the way in which these inputs go into this model is basically just in the form of a summation that you can see in this mathematical function sigma on the left, right? There is no weights here. This is the second drawback. And the third drawback is that this neuron fires only if there is a threshold, that threshold is set to 0. So taken together, this model, like, it was an extraordinary invention at that time for sure, because this is the first ever artificial simulation of a biological neuron, but it had all these drawbacks. So taking from this, Frank Rosenblatt, what he did was that he molded this entire thing in the form of an optimization problem and in the form of a machine architecture that can actually be trained and that actually can be implemented, right? And that's what led to the discovery of the perceptron in 1958. And perceptron was invented by Frank Rosenblatt in 1958, and it was actually designed. It was actually meant to serve as a machine, not really like an algorithm or a software. It was designed to be a machine, and that's exactly what happened with its with perceptron being built as a like a machine, as what we know as Mark I perceptron that was built in IBM by Rosenblatt, right? So now if you see the architecture of the perceptron, it has several changes from the McCulloch-Pitts neuron. So it took about 15 years to come to this point from the first ever simulation of a biological neuron. I can see that, here we have these different inputs x1, x2, xn, along with a constant 1. And now there are two changes that have happened. One, these inputs are no longer binary variables. They can be any type of variables, but like, binary, continuous, whatever. And along with that, each of these inputs are also now connected with certain weights, this W0, W1 up to Wn. And these weights can actually control the influence that each input feature would have on the final output. And this is exactly what we have been wanting, right? So that's what Frank Rosenblatt did. He connected each of these inputs with some weights. So, and then finally there was a weighted sum that was happening for all these input features. And then that weighted sum went to a certain function, a step function in the case of a perceptron, and then that finally went to an output. So this entire model was a breakthrough, right? Because now you could actually have an artificially simulated version of a biological neuron, and you can learn that neuron with data in a certain mathematical optimization framework by learning these weights and by minimizing a certain loss function, right? So this entire construct was first developed in the context of Rosenblatt's perceptron back in 1958. But the thing was that, and this is where it all began, right? As I was saying, and but the thing was that this kind of a model, like this perceptron, it basically served as a linear classifier, like a linear binary classifier, and it could only, this model could only solve linearly separable. It could only separate linearly separable patterns or learn linearly separable patterns, right? So, and like, something very similar to this note is what we know as logistic regression in statistical modeling. So logistic regression also has a very similar kind of an architecture. The only difference being that, you can think of it as in a certain probability distribution kind of a setting, and the way the entire problem is formulated in logistic regression is quite different from how it is formulated in the context of a perceptron, although the architectural similarity is quite high between a perceptron and a logistic regression model. Now comes the question, like, we know that, okay, a perceptron can learn linearly separable patterns from training data by optimizing this architecture and learning the optimal values of these weights W1, W0, W0, W1 up to Wn. And you can predict the output using this trained model. But then it only works for linearly separable patterns, right? Then what about the non-linearly separable patterns? Like, how can we learn them? And that's what led to the quest of a much more refined architecture that began in post 1958 after the invention of perceptron, and that being built into this Mark I perceptron machine of IBM. And that quest took quite some time. I mean, it was not easy, right? That quest took quite some time because people were struggling to understand, like, this is all good, right? I mean, you have this input features connected with weights. These weights finally get into a weighted sum. That weighted sum gets processed by a function, and that function spits out an output. And you can optimize this entire thing by minimizing a certain loss function, by a certain optimization algorithm. So that construct was already there. But then how can it learn more complex patterns from data? More complex patterns like nonlinear separation patterns from a certain data set that's given to it as an input. Data set on this input features and the output, I mean. So that led to the new invention, like, which, can you go to the next slide, please? So that's what led to the discovery of multi-layer perceptron. So you can see the standard architecture of a multi-layer perceptron here, which has overall, like, 3 layers, the input layer and 3 additional layers, the first hidden layer, the second hidden layer, and of course the output layer. And if you see the multi-layer perceptron architecture, and if you just take a very close look at it, you would just know it's just a collection of multiple perceptrons, right? And so, for example, just take any neuron in one of the hidden layers and just see all the incoming connections or incoming arrows that are coming towards that one neuron. You would see that that is nothing but a perceptron, as we saw in the previous slide, right? And all outgoing connections from a certain neuron basically represent that particular neurons impact on the next layer of neurons, right? So it's essentially a bunch of perceptrons that have been stacked together to come up with this network. And the logic behind that is because one perceptron can learn linearly separable patterns, right? So if you need to learn non-linear separation patterns, you would need multiple perceptrons to learn, like all those different lines that can come together to create a non-linear separation boundary between two different classes or multiple classes, depending on the problem. And that's what, that's what led to the invention of this multi-layer perceptron. Now, interestingly, Frank Rosenblatt gave a multi-layer perceptron model, not exactly like this, back in 1962 after the invention of his perceptron in 1958. But the problem with that was so his perceptron had an input layer, one hidden layer, and an output layer. Okay, but the problem was the hidden layer was not connected to the input and the output layers. I mean, it was just I mean, it was just like a hard-coded input layer, and Rosenblatt didn't know how to learn the input layer. But he knew this thing that multiple perceptrons should be taken together to create that kind of a network, and he came up with that idea. It's just that he didn't know how to optimize that, how to train that network or get the best version of it, as we see in this multi-layer perceptron architecture. So it is basically like this, that, when we need to learn nonlinear pattern separations, we need to learn a collection of multiple hyperplanes, so to say, because one perceptron can learn one hyperplane, multiple perceptrons together can learn multiple hyperplanes, thereby learning a highly nonlinear separation pattern between data very easily. Right, and that's the concept behind a multi-layer perceptron. So you have multiple perceptrons stacked together, one on top of the other in the same layer, and then you have multiple layers to get more and more refined information. And this is what actually set the context for what we know as deep learning today, right? And why it's deep, we all already know that it's not always deep though, because for example, this network is not at all a deep neural network. It is a shallow network, as we call it. That you have you just have like two hidden layers and an output layer. Okay. So so if you guys have any questions, just feel free to throw it in the chat. I'll try to answer it towards the end. Moving on from this point onwards, so this is a formal construct of deep learning, and once again, like Rosenblatt's perceptron, this method also came up with additional innovations associated with it. So first there was this, multi-layer perceptron architecture, as you see here, and then there was this algorithm called backpropagation, which could be used to actually optimize the loss function. So Rosenblatt's perceptron did not use a backpropagation algorithm. It was a different algorithm that was used to optimize that perceptron architecture to get those optimum values of the weights for perceptron. But multi-layer perceptron came along with an associated weight optimization algorithm, which is known as backpropagation. So, and backpropagation was originally invented by somebody else, although I mean, all of us by mistake know, Geoffrey Hinton is the inventor of backpropagation, but that's actually not true. He was the one who actually popularized it, so to say. But actual invention happened by somebody else, like some Frank Cinema, somebody, like way back. That's where the invention of backpropagation algorithm first happened. So moving on to the next slide, please. Okay, this is very important, and please ask me any questions if you don't understand the content of this particular slide. So we have already seen the perceptron. We have already seen the multi-layer perceptron, which is much more generalized architecture and much more powerful architecture than a perceptron. Now, how can we get different, like more other types of neural network architectures, right? So herein comes this concept of inductive biases, right? So inductive biases are nothing but assumptions that basically characterize a certain model architecture depending on the learning task. So if you have, for example, so what could be the task? It could be, say, sequence modeling, it could be, say, image classification or image segmentation, speech recognition, etc., etc. Now, a certain task in a certain real world problem setting, it actually needs some a specific set of inductive biases or assumptions to be injected in order to build the final and best model architecture for that particular problem. Okay. So, for example, RNN, recurrent neural network, was the first ever sequence to sequence neural net sequence input based neural network that was invented by Hopfield in 1982, who actually called it a Hopfield network. So it has all these inductive biases inside it, like a sequential bias. That means that RNN can only have one input at a time. Like it can only take one input in the sequence at a time and then goes to the next one. It can't take all of them together. It takes inputs one by one. So that's a sequential bias, the first inductive bias in an RNN architecture. Then you have memory bottleneck, which means that the way a recurrent neural network, I don't know if you guys know about recurrent neural network, but it's a sequence neural network which basically operates in the form of some hidden states that are connected to the input and the output in the form of a feedback loop. So if you unroll that loop, you get a long chain, or like a time sequence chain, and you can use a recurrent neural network for any sequence modeling task, right? And that could be anything, like any kind of sequential data. Exactly right. So you have this memory bottleneck inductive bias, which basically means that every neuron in a recurrent neural network can only take input from the previous hidden state, not directly the input from the previous input token or the previous input in that text. So that's a memory bottleneck inductive bias in RNN. Then we have recursion, obviously, this thing that is this feedback loop that's there. Once you unroll, you get the entire chain. That's the third inductive bias. CNN was another invention which came after RNN by Ian LeCun, the Meta chief AI scientist, in 1998. And it also has several inductive biases like locality, translational equivariance, which is basically the weight sharing. That means, in every image you have you are basically sliding the same convolution kernel that has the same set of weights across the entire image, across all sections of the image that you are feeding as an input to a CNN architecture. So this basically means that you are using the same weights as in that convolution kernel to learn different parts of the image. That's what weight sharing means, and this actually is equivalent to translational equivariance, which basically means that you can learn to connect the object in an input image to the designated output, regardless of which particular place of the image that object belongs to. That's what translational equivariance means, which is actually implemented in a CNN architecture by this weight sharing mechanism. That means using the same convolution kernel metrics to slide over the entire image. And then we have translational invariance, which means that the entire learning would be happening the same regardless of if the image has undergone a certain kind of translation. And that's exactly what happens when you do this pooling operation in a CNN network. So CNN network has a bunch of repeated operations, right? Convolution pooling, like that, right? So convolution takes care of the translational equivariance, pooling takes care of the translational invariance. And locality is of course, what it means is that you're assuming in a CNN network that every pixel in that image is strongly correlated to its associated pixels that are in the neighborhood of that pixel. That's a locality inductive bias, a locality assumption. So I'm saying these things because these are very important foundational concepts, so to say, in deep learning and AI, that you need to have different sets of inductive biases to come up with different neural network architectures. For example, RNN has a particular specific set of inductive biases. CNN has another set of inductive biases. And like that, there are different architectures that have different other sets of inductive biases. So you can see this diagram down below, which actually illustrates like when should you have like more strong. Now there could be two kinds of inductive biases, right? One is a very hard inductive bias, which is like a strong assumption about the model architecture. Another could be like a soft inductive bias, which is like a weaker assumption on the model architecture, like a weaker assumption. Now, when do you use hard inductive biases and when do you use soft inductive biases, right? That totally depends on how much data you have for training the model. If you have For example, in this case, in this diagram that I found in an online article, it's very interesting. It's like, here hypothesis space it basically means the space of all models. Okay, basically means the space of all models, or space of all model architectures, so to say, that you can build based on the training data that you have in hand. So so you have this training data. So you can see on the left, left diagram where the training data size is very small. So when you have like a small training data set, you need strong inductive biases to get to the right good optimum solution by performing the optimization. And when your data set is large, comparatively large, then you can use soft inductive biases, and that will also lead to the good optimum solution. So I mean, that's exactly what happens. And this sets the ground for the next slide, which is what transformers is. So that basically means that transformers is a neural network architecture that has the smallest set of inductive biases. That means it doesn't have any strong inductive bias, and that's what makes it so much flexible and so much adaptable to a wide variety of real world supervised or unsupervised learning settings. So can you go to the next slide, please? So this is the transformers architecture. If you guys are not following along, please feel free to ask me any questions, and you don't have to, like bang your head with these architectures in our constructs and everything, because transformers is a complex architecture. But I would just like you to remember this thing that, like how this thing works in reality. So transformers at the end of the day is based on a concept called self-attention, okay, which is mathematically implemented in the form of something called a scaled dot product attention. And a scaled dot product attention is nothing more than a statistical correlation between two variables. Okay. So in a transformer architecture, you basically have two main blocks. One is an encoder block, which basically encodes information based on the input that is given to it. And then you have the decoder block, which basically decodes that information to finally create a certain output. Okay. And inside each of these two blocks, you have three things going on. You have a query, you have a key, and you have a value. Now, what do these three things mean? So in the context of a certain sequence, any kind of sequence that you can imagine, for every input, suppose we have a sentence of say 5 words, say, I want to go to Switzerland tomorrow. So this is a sentence, right? So now each word in this sentence has a certain semantic context, and it has a certain kind of a relationship with the associated with the other words that are in the neighborhood of this particular word that I just said. So how can you capture this context in the best possible way? You can do that by computing something called an attention score, or an attention weight, or more specifically a self-attention weight. And the way it's done is by optimizing the correlation between a certain query and a possible certain answer for that query, which is the key, right? So you have the Q, the query, you have the key, the K, and the correlation between them is what you see in this attention function softmax of, before inside the softmax, like Q and K transpose. Q is the query, K is the key, and DK is nothing but the dimension of the input embedding, which is what you feed as an input to the model. And V is basically the value, which is a representation of a certain word in the input sentence. So taken together, this softmax operated on this normalized, uh, statistical correlation, which is QK transpose, is what we know as scale dot product attention, and then we multiply it by the the values, which is a representation of the input text elements, and then we get the attention score. And that's how the entire layer is designed. You can see, there. And I would like to touch upon, this is one attention. Now you can ask different queries, right? So for example, if I say that, okay, I want to go to Switzerland tomorrow, so every word, say I am saying that, Switzerland is a word. Now you can ask different queries related to Switzerland, and that will in turn lead to different answers, different best possible answers. So when you are asking multiple queries, you can think of each query as a particular head, and different queries would lead to different heads. And overall, when you combine all these heads together, and that's what exactly we mean by multi-head attention, where each head corresponds to a certain kind of query, and then you combine the inputs from all these heads from this multi-head attention to one final output that is finally connected to your end output in the form of a, like a softmax function or a linear neural network. You can ensure that you are capturing each and every input token in the sentence that you have fed as an input in all its contexts. And that's what makes this architecture so much powerful in a wide variety of applications, right? So going to the next slide, please, the last slide. So this is just an illustration of all the transformers-based models that are out there now. You have GPT-3, you have Lambda from Google, you have Palm, once again from Google, BlenderBot, Galactica from Facebook, right? And you have Megatron from NVIDIA and lots of others, right? So UL2 is also from Google, and the parameter sizes vary from this model. I mean, it ranges from like 10 billion to like 175 billion to 540 billion for Palm, and right, like that. So all these models, and there would be many more coming in the coming months and years. So there's a very active research field at the moment, but all these models are basically based on that seminal work of transformers that I just discussed in the previous slide, right? So you can follow along all these models very well. You can read about them if you just understand the transformers architecture and this self-attention incorporated by scale.product attention and the way it works, very well. So that's what I would say, and that ends my presentation. I would now open the floor to questions if there are any.
Yeah, that was a really interesting session, by the way. And there were some points that I just wanted to mention out for the students, and I wanted to get your point of view on those
Sure.
points as well, because it's been a really sort of a right journey that you have taken us through, yeah, from the entire history and those things. So from the history and for the literature that I have read, well, the little that I have read, I've seen that the specific backpropagation algorithm was really a breakthrough
Yeah,
in going
of
from a
course.
single perceptron to a multi-layered
Yeah,
perceptron sort of
yeah,
architecture. So can you explain that uh, for our students, because that is sort of a black
sure.
box right now, right?
Yeah. Okay, sure. Well, thanks for bringing that out. So, see, I mean, back propagation, as I said, so I mean, it basically originated from Rosenblatt itself. So, I would like to, this is very interesting a story. So, after Rosenblatt invented perceptron, as I said, Rosenblatt also gave a multi-layer perceptron model of his own in 1962. But that model was just a three-layer network, like an input layer, as I said, one hidden layer, and the output layer. That's it. But the hidden layer, they had some already pre-assigned weights, and those weights were not learnable with the input training data. And Rosenblatt didn't know how to learn those weights, but he knew this thing that he needed to. So every time you feed the input, right? So how does a neural network work? So you feed an input, it goes through a series of layers, through a series of mathematical transformations, which is essentially a bunch of matrix multiplications with weights and the inputs and the activations. And then you compute activation function, and then you go to the next layer. And like that, it moves forward. So at the end, you get that output. So, and then you compute the error that you had by subtracting that output from its actual value. So you get the error, right? So just give,
Hmm. Yeah, sure.
and so Rosenblatt knew this thing that he had to somehow propagate this error backwards. In fact, this thing of error propagating backwards was actually first said by Rosenblatt himself. So, but
Hmm.
he did not know how to do that. So then followed a series of works, and there was somebody named Frank Sinema, who is actually the original inventor of backpropagation. So what he did was that he came up with this entire thing of, so like, it's a simple thing. You have an input, you take it through the entire forward pass of the entire neural network, one after the other, which basically means that you either feed the actual input x1, x2, whatever in its original form, or you compute some embeddings out of the input in the data, and then you feed those embeddings as an input. Whatever you do, then those embeddings go through this series of layers, getting transformed and activated
Mhm.
inside every neuron, and then you get to the final output. Then you come to the loss, right? So you figure out a certain loss function that you want to compute. So if it's a classification problem, you take something like a cross entropy loss. If it is a regression problem, then you take something like a least squares loss, or like a mean
Mhm. Yeah.
squared error or something like that, right? So that gives you the loss function. That tells you, okay, how much was my error with this first pass, with this set of weights, and you start with an initial set of weights for this neural network, and you get that loss function. So the entire idea of backpropagation was that to optimize this loss function, and then by to use the chain rule of derivatives, which was invented back in the 17th century by Leibniz, Frank Leibniz, the famous mathematician,
Mhm.
to propagate the error that was conducted backwards towards in the backwards direction from the output to the initial layer of the multi-layer perceptron. And that's exactly what led to backpropagation. That means it's
Yeah. Yeah.
totally the chain rule that's playing along. So if you understand chain rule of derivatives in high school calculus, I mean, backpropagation would be key for you. I mean, like a piece of cake for you. I mean, and I would like to call out one thing very clearly here. I would really encourage all the people here attending this talk to not think of deep learning as a black box. Initially, trust me, since I came from a statistics background, I also used to think of deep learning as a black box. But trust me, it is so not a black box. In fact, it's a beautiful architecture. It's a beautiful mechanism that goes inside it, that's based on like foundational mathematical principles. And those principles are linear algebra, like mathematical optimization, like functional transformations and like that. So if you understand linear algebra and multivariable calculus really well, deep learning will just be a piece of cake for you, because that's in the end that's exactly what it's doing. So this all these neurons that you see stacked up in the same layer, right? And then there are activations, then goes to the next layer. So there are essentially three things that are happening. The first thing is that there is a loss function that you want to minimize. There is an activation that can transform an input coming to it to something else, to another output that then gets fed to the next input, to the next neuron in the next layer, and like that it goes on. Very similar to how a biological neuron works, right?
Yeah. Yeah.
So
That was the basic idea, right? Yeah.
yeah,
The inspiration.
and in the end, this actually ends up, if you see it mathematically, a deep neural network model or a neural network model in the end just fits a highly complicated curve to a series of points. That's what it does. And the way it does is by the use of these multiple layers, and by using different kinds of activation functions. And that's the way in which that non-linearity is incorporated in the final output of a neural network model, right? So
Hmm. Yeah. Kiri. And we have another very interesting question from Vibhuti. So he's asking it, why did it take so long for people to come up with models like or applications like ChatGPT? So what were the actual foundation for AI up till now,
sure.
since we having a recent boom in this field?
Yeah, so that's a great question. So I would say that there were multiple reasons behind it. First of all, what we know as very famous, there's AI winter that happened sometime, I would say in the phase of 1960s to 1980s, or even after that, yeah, something like that. So that phase, and even the part before that, there were two major roadblocks. One was that the amount of training data that could be gathered was very minimal. It was not what it is now, at least for say ChatGPT or something like that. This was the first roadblock. The second was that the compute infrastructure was not that advanced as it is now, right? So there were no GPUs, there were no TPUs, there were no this kinds of all this kind of hi-fi compute architectures that we have now. So these two things taken together, you know, caused all these roadblocks, created all these roadblocks for this AI advancement to happen all this time. And if you specifically talk about ChatGPT's rapid, success, so that is totally driven by two things, I would say. So I don't think many people know about this thing, but I mean, people see ChatGPT, they see OpenAI, but actually the foundational innovation that runs at the back of ChatGPT was done in Google way back in 2017 when this transformers paper came out by a team of researchers in Google Brain, which was led by, I think, Ashish Vaswani. So this guy is a professor of computer science at the Stanford University and also a scientist in Google Brain. So he invented transformers, where for the first time this idea of self-attention incorporated as a scale dot product attention was introduced. And this was a seminal work, because this thing didn't happen earlier. So if you see the neural networks before transformers, we had RNNs, we had CNNs, and these, as I was saying before, RNNs and CNNs use their own specific set of inductive biases, and they had their own fields of application, and you could only do a range of tasks with this, not like very specific tasks, so to say, not a wide range of tasks. Like for example, RNN is mostly for sequential models, but as I say that, it has this inductive bias of, the sequence thing, that it only takes one input at a time. You feed an input, and then comes the next input, and it goes like that. And so there is only a certain type of problems that it can solve. CNN, once again, it can solve image recognition, image classification problems, and it has in its own set of inductive biases. But transformers was the first ever network with this introduction of the self-attention mechanism, with the scale dot product attention concept, which was, I would say, free from any inductive biases. So that's what made it so much generalized, so much more flexible, and so that if you have a large amount of data, you can learn a lot of things from a transformers architecture or a model based on a transformers architecture, right? And that's exactly what powers ChatGPT, where GPT-3 is basically the model, and these days GPT-4 is basically the model that runs at the back end. So GPT is nothing but generative pre-trained transformer, right? So it is nothing but a transformer model. But I want you to remember that in the original transformers paper, there were both an encoder block and a decoder block, whereas in GPT you just have the decoder block, and that there is a reason for it, because you don't need both the two blocks all the time. You need different blocks for different tasks. Both have the transformer self-attention mechanism running inside it, so that query key value thing and their self-attention to create that attention score is inside the encoder block also, and that is inside the decoder block also. But depending on the task, you use a particular kind of block. So if you want to encode an input, into an embedding that could be connected to a certain output, say you're doing a classification problem or say a regression problem, you use an encoder based transformer, like for example BERT. Whereas if you want to do something else, like say natural language generation or natural language understanding, you use or sequence question answering like we have in ChatGPT. Then you use a decoder based block, because that's what decodes it into the final output sequence. It generates a sequence for you. So
Great. I guess that was really well explained. So Vibhuti, I hope that you got your answer. And thanks for the interesting question as well. And as always, we would love, right, to extend this to another hour, because we are getting some interesting conversation here. But as the students have their regular sessions after this, so I guess this is where we should have our hard stop. We just have one more question that I just saw
sure.
from Suryakanti. I guess that this won't take much time, and this is, I believe, a genuine query from her side. So she's asking that why can you please explain a bit about the inductive biases that you talked about?
Yeah, sure.
Yes. So why
Uh,
not we go back to that slide, right?
yeah, sure, please.
Yeah.
Okay. So see, inductive bias, as I said, is just a fancy term for in machine learning what we in statistics call as assumption, simply an assumption, right? So every model that you want to fit for a certain learning task, be it a supervised learning task, semi-supervised or unsupervised learning task, it comes with a certain set of assumptions, right? So for example, if you're talking about linear regression, there are multiple assumptions in a linear regression model. And each of these assumption is called an inductive bias. Okay. That means you are inducing a certain bias that your model will have towards something, right? That's why it's called inductive bias. And that bias will characterize that particular model architecture. So in a linear regression, the first inductive bias is that it has to be a linear combination, right? It's linear. And then you have, like, these different features that are there, their impacts are also incorporated in a linear fashion. Linear, like additivity, you have another inductive bias, and like that, the errors has to be, mean zero variance constant. That is another inductive bias in linear regression. So every model has a set of assumptions, or AKA a set of inductive bias. And as I was saying, that depending, and this thing is actually very important, as I was saying, in the context of uh, any modeling task, in the sense that you need to know that which, and this will help you figure out the right model architecture for solving a certain learning task. Because if you don't know inductive, like if you don't know what inductive biases are, you need to inject into your model architecture, or what assumptions you need your model architecture to be based upon, you would fail to come up with the right model architecture to solve a certain learning task. So for example, say in CNNs needed that particular set of inductive biases, like locality, like translational equivariance, as in weight sharing, translational invariance with the pooling thing, so that it could classify like a wide variety of images, right? And as you know, like CNN, it solved the ImageNet challenge like very well, like architectures based on
Yeah.
CNN, right? So that's what I would say. I mean, let me know if you have any other question.
Yeah, great. I guess again, very well explained. And I hope that all the students enjoyed the talk as much as I did. Very informative, and thank you for joining in. From behalf of the entire team and all the students that are currently there, and I would just like to thank you once again. Lovely
Same,
to hear from you. Great
same
session.
here. Thanks
Thank you.
everybody for your time. Thank you. Bye.
Okay, guys, I hope you all liked the session. As I just said, I'll just share the feedback form in the chat so that you guys can fill that up and you can move on to your regular sessions. For LinkedIn, you can just go over to the LinkedIn. You can share his profile. He's very active on that platform. So I encourage you guys to just go and have a look at it. There you go. The feedback forms in the chat. Based on the filling of this particular form, we'll send out the participation certificates. Yeah, sure, Harshan. We'll have another session on this topic. And I hope you guys liked it. Great. So if you have a regular sessions, you can move on.
I have floated the feedback form in the chat section.